number previously available. We use these spectra to colour the asteroids. These colours depend on the chemical composition of the asteroid surfaces. The colours here are strongly exaggerated. We now quickly leave the plane of our solar system and look at it from above. Gaia's catalogue of solar system objects contains trans-Neptunian objects, near-Earth asteroids, and also 31 moons of planets in our solar system. But most of the Gaia-observed asteroids orbit the Sun between Mars and Jupiter. Different groups of asteroids with common origins are investigated now. First, we show the Vesta family, a group of asteroids with similar orbits and colours. The members of individual families are thought to be fragments of past asteroid collisions. In this case, a major impact with the large asteroid Vesta has created these fragments. Next, the members of the Flora family are highlighted, showing a much redder colour. And finally, the Themis family, blue in colour and in a much larger orbit than the Vesta and Flora families. Now we move down to the plane of our solar system. The three asteroid families are shown from this perspective. First, the Vesta family. Next, the members of the Flora family. And finally, the blue Themis asteroids. Gaia's catalogue of solar system objects brings a wealth of data for many asteroids.
I see it. That is amazing. Whoa, that is so cool.
Hello everyone, this is Scott Roberts from Explore Scientific and the Explore Alliance, and we are proud to announce the 126th Global Star Party with the theme of light and color. There's a little quote here. In art, as in science, reductionism does not trivialize our perception of color, light, and perspective, but allows us to see each more of these components in a new way. That was from Eric Kandel. But light and color are of paramount importance to astronomers. They provide us with a wealth of information about celestial objects, their properties, and their processes. You're going to hear tonight from our presenters, various aspects of light and color as they relate to the universe and to ourselves. And so kicking off tonight's program will be David Levy, who will give his usual poetry and insight into astronomy and this global star party. This will be followed up with David Eicher, who will have his Dave's Exotic Universe. He is looking for, and the magazine, Astronomy magazine, where he's the editor-in-chief, definitely are looking for things to talk about that are unusual, that amateur astronomers can study, and there's a whole ton of stuff out there that amateurs really don't touch on much. So you'll want to learn more about what he's talking about tonight, and I think you'll find it enjoyable. Don Knabb will join us from the Astronomical League, and then that will be followed up with León García. Now León is how you pronounce it. He is one of the first place winners of the National Young Astronomers Award that is also supported by the Astronomical League. Explore Scientific is one of the underwriters of that award, and so we're proud to have him on our program. And then Maxi Falieres will be on with his astrophotography. Maxi does some amazing stuff from his home in Argentina. Tom Field joins us tonight. Tom is the author of some software called RSpec, and he has a very inexpensive solution to doing spectroscopy with your telescope, virtually any telescope that you might own. So very cool. We'll take a 10-minute break, and then we come back with Cesar Brollo from Argentina and his Southern Sky Astronomy from his balcony. Adrian Bradley with his Chasing Dark Skies will be on. Marcelo Souza from Brazil will join us as well, talking about astronomy outreach in Brazil. And then we finish off with Michael Carroll. Now, Michael is an incredible author and space artist, and we always love having him on. Anyways, we hope you really enjoy it tonight, and I'll turn this over to David Levy.
Well, thank you, Scott. It's great to be here. And although my quotation will not be specifically on light and color, it will relate to it, as I will explain why. Light and color can mean many, many things. I think for most of us, it has to do with the spectrum of the stars, O, B, A, F, G, K, M, etc., and R, N, and S, and all of that. But my first association with light and color was in 1959, after a thunderstorm near Montreal, and Mom told me to look at the rainbow. It was my first rainbow, and it was also the subject of one of my first books. I do not have that book anymore. It was only 3 pages long, and it was awful. But anyway, that was my first rainbow. The second thing for light and color was a telescope, and there's quite a story to my 8-inch reflector. I was at the observatory of the Montreal Centre of the Royal Astronomical Society of Canada, and we were just about to go home, and I looked at a few kids my own age, and I said, "Would you like to come over to my place and look through a 3.5-inch telescope?" At which point an older member said, "Would you like to come over to my place and look through an 8-inch telescope?" And we couldn't resist that. We had a wonderful night over at his place looking through that 8-inch at Jupiter and other things. Then I went home, and about a week later, I got a phone call from David. And he said, "I'm going to have the telescope out tonight. I was wondering if you would like to come in with me." And I said yes, and I took the bus over to his house. And we had a wonderful observing session. And I was really impressed with how that telescope showed the planets. And he kind of told me that it was his habit when he went to college to lend his telescope to someone who he thought could make use of it. And he asked me what I had done with my 3.5-inch telescope. And I told him, well, I looked at the planets and Jupiter, Saturn, and a few of the deep sky objects. I found SJ31 with it. And he said, "What about the moon?" And I said, "Oh, yeah, I've completed the lunar training program." And David said, "You saw all 300 craters?" And I said, "Yes. And the valleys and mountains that are labeled A to Z here in the United States." And he said, "You did all that with the 3.5-inch telescope?" And I said, "Yes." He said, "David, you just borrowed yourself an 8-inch telescope." And he drove it to my house that night. And I was in heaven, I got to tell you. And that was 59 years ago. I still have that telescope. I discovered a comet with it in 1987.
Wow.
And it is the only telescope other than Miranda with which I've discovered comets. Which brings me to the quote, which comes to yet another aspect of light and color. And this refers to one of the most colorful people in science I've ever known. And that was Robert Oppenheimer. And the movie is playing right now. I strongly recommend it. Any of you who have not seen it yet, It's not a perfect movie, and you need to pay attention, but I found the physics very well explained. And the reason it was well explained was that he would explain a few lines on his blackboard, and then he'd get emotional about something. And it was the insertion of emotion into his explanations that really got to me. And one of the scenes in that movie had to do, in fact, one of the major aspects of the movie, the major portion, had to do with Trinity Site, where Oppenheimer is planning the first detonation of an atomic bomb to usher in the nuclear age. And, he was asked, well, what do you want to name the site? He said, I want to name it Trinity Site. And he said, why do you want to call it Trinity? After John Donne. And here's the first of the quotes from John Donne: a hymn to God, my God, in my sickness. As west and east in all flat maps, and I am one, are one. So death doth touch the resurrection. I mean, and that's kind of a stretch to relate that to the Trinity Site. But then he came up with one that was far more obvious also for John Donne. Batter my heart, three-personed God. I mean, the Father, the Son, and the Holy Ghost. And that relates directly to the Trinity. And finally, at the moment of detonation of the atomic bomb, the first atomic bomb in the history of the world, he stands up and he says, I am become death, the destroyer. And so these quotations are from, let's see, we have John Donne, a hymn to God, my God, in my sickness. Three-person to God is from Holy Sonnet 14. And I am become death is from the Hindu scripture, from the Bhagavad Gita. And there's a lot of light, a lot of color. I think he was one of the most wonderful scientists who ever lived. He got treated horribly afterwards. And I'm going to give you a little bit of a spoiler alert, but not really. It's not going to ruin the movie for you. It's the last scene, the last thing that is said in the movie. And there's a scene at the end where he is meeting with Albert Einstein. And he goes up and the two men start to talk. And he says, do you remember when we were just planning this? Einstein says, yes. And he said, remember I asked you if you thought that it would ignite, the nuclear explosion would ignite the atmosphere? And Einstein said, yes. And I said, probably not. And then Oppenheimer looks at Einstein and said, I think it did. And that's how the movie ends. That is a wonderful, wonderful movie. There's a lot of light and an awful lot of color in it, and I recommend it very strongly. And on that note, back to Scotty Roberts.
Okay, great. Well, there's, it's great to have all of our presenters on Global Star Party. They come on each week that we do this program and share all their knowledge with you. It's it's wonderful also to have this live audience, that interacts with us and asks such interesting questions, and also help me as a broadcaster to sometimes fix my little mistakes. So we had started off with not being turned on with YouTube, but I was able to catch it due to the help of Mike Wiesner. So Mike, thank you very much. I also want to thank Springer Books. Springer sends me, review editions of these of their Patrick Moore series here, and there's one about the Barnard objects with Tim Hunter and Gerald O. Dobeck and James McGahey. So that is a great book. And then Michael O'Brien, a deep sky astrophotography primer. So you want to check into that. And I also want to mention that we're coming back with Dr. Daniel Barth's How Do You Know series. And so that will start on this month on the 21st. And also Gary Palmer, who is a regular contributor to Global Star Party, is offering a class that you can find on the explorescientific.com website. It's called the Solar Experience with Gary Palmer. So if you're gearing up to go and do eclipse photography, or you want to learn more about photographing the sun, Gary Palmer's your man. So anyways, again, thanks for tuning in. Our next speaker is none other than David Eicher. David is the editor-in-chief of Astronomy magazine that is celebrating their 50th anniversary. And so it's a banner year for the magazine, and the magazine also is about to publish a special edition on the eclipses that are coming up. So you're going to want to definitely get into that. And David is a friend to all amateur astronomers. He's certainly one of my great friends too. And David, thanks for coming on to Global Star Party and sharing your exotic universe with us.
Thank you, Scott, for having me once again, despite the fact that you know me and what I'm all about, and yet you have me back again. This is really a testament to you, Scott, in a very strong way. And I had a couple of comments before I get into my object of the night. One thing that was really great, I thought, was that introductory video that you chose that showed us asteroid families. And of course, we're in the very early days of understanding. It's an extremely complex problem to understand the origin of meteorites and where they came from specifically. This is an early phase of that as a science, as a part of planetary science. But I thought it's maybe worth mentioning, because some of the asteroid families were mentioned there, that if there are collectors out there, that is very exciting for us all, to have pieces of the ancient solar system. There's a related set of meteorites called the HED family. The Howardites, the Eucrites, and the Diogenites, HED family of meteorites. And those are known to come from the asteroid Vesta. That's one of the largest asteroids in the main belt, the asteroid 4 Vesta. So you can get one of these relatively easily and have, with no doubt, a piece of Vesta in your hands. That's a pretty cool thing.
That's pretty cool.
For planetary science, and tying back to that great video that you showed us. And I would also agree with David. I saw the Oppenheimer film, and I thought it was really good and very inspiring. And it's long. It's about 3 hours, but it has to be, because there's so much story to tell. And I thought the opening and closing with Einstein, that was just really done magnificently well. There's a lot of drama associated with Oppenheimer. Of course, he was out at the Los Alamos group. And I have a short quiz for you, because my father, some of you might know, my father, John, was a Manhattan Project scientist, and he worked at Columbia with Harold Urey, Harold Urey there at the original group there in Manhattan. And they worked on the bomb that became the Hiroshima bomb. And of course, the Los Alamos group worked on the plutonium bombs rather than the uranium bombs, which the Eastern group worked on. So there's a question here. The plutonium bombs were developed slightly later, and yet the Trinity test, David, as you said, was the first detonation of an atomic bomb. And why did they test that bomb in New Mexico is the question there.
Okay, I think the answer to that, and I visited Trinity site, and I think the answer is obvious, that they wanted a place far away from anybody. They actually probably could have chosen a place more remote, but it would have been pretty difficult. But about 30 miles or so southeast of Socorro is a pretty isolated area.
Well, you're right about that, David, as far as the location. I was meaning, why did they need to test the plutonium bomb rather than the uranium bomb that they had earlier?
Yeah, I kind of think that the uranium one, they figured, couldn't fail. It didn't really need to be tested, but the plutonium one, Oppenheimer insisted that they do a test of at least one of those.
You're right about that. And the reason is the triggering mechanism. So the uranium bomb, which ended up being the Hiroshima, the first one dropped, had a very simple gun trigger mechanism to detonate it. The plutonium bomb had a much more complex mechanism to set it off. And that's why it had to be tested first, although it was developed, if you will, second by the Los Alamos group. And of course, the nuclear material for the Trinity group, for the Los Alamos group, was made at Hanford. And one of the primary things that my father worked on was the scaling and the figuring out of the Oak Ridge plant, which produced the material for the Hiroshima bomb. Hanford now of course, ends up now being important governmental land way out on the edge of one part of the United States as one of the locations for the 2 LIGO detectors. Now that we're not making, atomic bombs to do, well, we stockpiled them, but, now that we're not actively making, plutonium bombs, we have a LIGO detector, of course, at Hanford and also down in Louisiana, because it's the right distance from Hanford, where some of us just visited for Alcon there. So anyway, that's my long detour there. Forgive me for that, but it's an interesting thing that doesn't get talked about too much, why the timing of the 2 atomic bombs worked out the way it did.
Thanks, David. So that was really very special.
There you go. You get more useless information from me than you ever could want. Okay, sorry, David.
My daughter's dad worked on the Trinity site.
Is that right? I don't think I ever knew that.
Yeah, he worked at the Trinity site. He showed me a glass encased piece of trinitite that he had with him. And I think he was going to give me one, but I don't seem to have it here. So maybe I need to ask him again, or maybe I didn't want it for obvious reasons.
And I have a piece of trinitite, a fairly sizable piece in the basement. It's fairly common stuff if you want to get a hold of it. And it's actually reasonably weakly radioactive compared to a lot of very hot specimens of natural radioactive minerals like uraninite and so on. So it's not super radioactive, but you wouldn't want to carry it around in your pocket, for 6 months.
No, you certainly wouldn't. And
as Marie Curie demonstrated,
Yeah, and the interesting thing is when I was at Trinity site, I was overwhelmed at the monument, the obelisk that was right at ground zero. I was just overwhelmed with emotion when I saw that.
It's a pretty special place to visit. And I think last I remember, maybe they've changed, I think it's only open sort of for visitation, something like maybe once a month or something like that.
Twice a year.
Once a year now.
Twice a year.
Wow. Okay. Because it used to be open more frequently. Wow. Yeah. So times have changed.
So they're being more careful.
Yeah. Yep. But it's sort of a yellowish, greenish, glass. The desert sand was melted into. That's this new mineral specimen, trinitite.
Yeah. Wallace Ronald Delvaux, who's watching on Facebook, says, my father-in-law witnessed a nuke go off as a Marine in Nevada in a trench.
Wow.
Yeah. And I had a science teacher in high school that did the same thing. I'm very curious that they were together. He described that whole event, and from my science teacher's explanation was that you entered into the trench and it went down. He told us how many feet it went down. It went down a long ways, then turned at a right angle, and then went down again, and then turned at a right angle again. So by the time they were at the bottom of this thing, he said you could not see your hand in front of your face. Okay? There was some trees and stuff that was in front of the trench, as he described it. And he said they told them to get into almost like a fetal position, okay, on the countdown, and to keep their eyes shut. And he said, so what did I do? My teacher said, I stood up and kept my eyes wide open. And he said, when that thing let off, he said it was blinding white light inside the trench, and he was knocked onto his bum from the shock of the explosion. So,
Wow.
and when
Could
he
I
got
interrupt
up out of the
David for a
trench, he said
second?
that tree was just like vapor; it was gone.
Mm,
So,
May I interrupt David for just a second?
of course.
Yeah, I was in light and color. I was going to add something else relating to the theme of today. Dean Koenig came to observe with me one night, about maybe 10 years ago. And it was a winter night, and we had a number of powerful telescopes up there. And he had like a 15-inch or a 16-inch. And he said, well, I can detect color in the Orion Nebula. And I said, so can I. And he said, what telescope are you using? I said, the 8-inch Pegasus. And he said, let me see that. You can't see color with an 8-inch telescope. And he looked at the telescope and he saw beautiful reds and blues in the Orion Nebula with an 8-inch. He said, David, I may have to call the police. This telescope is illegally good. I just wanted to share that with you.
Nice. Well, someday I have a couple boxes of artifacts from my father. Someday I'll catalog all this stuff and make some sense of it from the Manhattan Project. And I'll tell one more story about it from Columbia, which was actually before they moved uptown to what was called the Nash Building in Manhattan. The project started in what is now the Columbia University Physics Building that has an observatory on the roof now in New York there. But they had a number of meetings off and on with the guy who was running the program, who was Leslie Groves, the Major General. They made him, and you know why they made him a Major General? He was in the movie, of course, David. He was a big, heavy, fat, sloppy guy with his disheveled uniform all the time. But he built prior to the Manhattan Project, which was, of course, inspired by Einstein's letter, he built the Pentagon, and he built it ahead of schedule and under budget. So Roosevelt said, that's my guy to run the Manhattan Project. But he was in some meetings, and my dad, as a young scientist, he was 21 years old at the time when he started, my dad, but he wondered, were there two aides who went everywhere with Groves? If he went to the bathroom, these guys went along with him to the bathroom and back. And it turned out that he had a checkbook, Groves, who was running the whole program, the Manhattan Project, with an unlimited government income in it. If they needed, platinum wire or whatever they needed on the spot, he would write a check for it, So they wanted to make sure that checkbook in those days in 1942 didn't get lost. So these guys shadowed him everywhere he went. So anyway, there are lots of Manhattan Project stories, but someday I'll share some of the relics that I have from those days with you, if you'd like.
thank you.
But for the moment, we'll go much farther afield, and I will, I got to get back to here, and I will share my screen and share the right screen, and I will start a slideshow if I can. And do you see Centaurus A?
Yes.
Good, you're seeing the right thing. Excellent. Okay, that's good. So there's, in 7 billion years from now, when the Andromeda Galaxy and Milky Way merge, we may look something like that. But for the moment here, we will talk about Father Lucian J. Kemble, who was around back in the early days in the 1970s and 80s. He was an early subscriber to Deep Sky Monthly, my little amateur publication. And he noticed some asterisms around in the sky, and he wrote the famous columnist, who was a friend of mine and a good friend of David's, Walter Scott Houston, who of course wrote his famous column for many years, Deep Sky Wonders in Sky and Telescope, about a very notable sort of flowing line or cascade of stars that he saw in the constellation Camelopardalis. This came to be called Kemble's Cascade, as a very nice and bright and fairly large asterism. It spans about 3 degrees across overall. It terminates on one end with a very nice and bright, compact open cluster, NGC 1502. And what makes it really alluring, and I can tell you that I'm being honest here, Scott, because I'm talking about a colorful set of stars that show many colors, and as stars, they're all emanating light. They're all producing light. So there's light and color involved here. So I'm remaining honest.
You are
here.
remaining honest.
So for a change, so there are about 20 stars in Kemble's cascade, and they range from magnitude 5 to about 10. It's a really pretty field, and you can see why Father Kemble really liked this area. He was a binocular and small telescope observer, and there's some bluish stars in the area and some nice orange suns as well. He was a Franciscan friar, and he wrote Scotty Houston that this is a beautiful cascade of faint stars tumbling from the northwest down to the open cluster NGC 1502. And so Kemble's cascade was born. 1502 itself, which is, as I said, a nice compact cluster, it has about 60 dozen stars. It's a young cluster. It's 5 million years old. About 10 arc minutes across and sixth magnitude and about 3,500 light years away. So it's a nice open cluster in and of itself. And I will show you from Ron Stoyan's atlas here, the Kemble's Cascade portion of a chart with Cascade nicely written out in German here. And you can see, I haven't looked into this or really found it elsewhere. The cluster here is called the Golden Harp Cluster, NGC 1502, and all I can do is think, geez, people have more time to come up with these names than is believable. But anyway, it's in a nice field in the far north. Here's an image of Kemble's Cascade. This is by Walter McDonald, and you can see the bright knot at lower left here is NGC 1502. This is a pretty sizable chunk of sky here, showing the whole thing. And here's a later image by Greg Parker and Noel Carboni. And you can see again 1502 over on the left edge there. And you can see really nicely the star colors that are in the cascade of stars here that I think caught Father Kemble's attention originally.
It's interesting that he calls it the cascade, because you really get the sense when you look at those pictures that the stars are flowing into the cluster. It's really
You do, and he was a very nice guy. I corresponded with him. I think he was at Stellafane maybe a year or two way back when, but he was a very nice guy and sent letters to the editor, not only to Scotty and also to Deep Sky Monthly back in the day. So very enthusiastic and talented observer. He also made some drawings, and I might actually have some of them still in the file of his. And he passed away, I think it was 20 years ago now or so. But he was a very astute and analytical observer, if you will, with small telescopes back in the day. And this is a close-up shot of NGC 1502, just to kind of show you what a tight knot of an open cluster this is, fairly small group, but bright, sort of a dazzling little group of diamonds here. So this is a good object to go after and to look at. And especially if you're thinking, well, the far northern sky really doesn't have anything that's very exciting, but it does. It has a few interesting and unique things like Kemble's Cascade. I'll tell you, thanks, Scotty, for mentioning this, but we're in the latter stages now of our 50th anniversary year with the magazine. Here's the one that will be coming to you relatively soon with a bunch of diverse topics. Michael Bakich and I have this book out. I've mentioned A Child's Introduction to Space Exploration that is out there now. And we're excited. And we have Scotty involved. And I think, David, you're going to come and speak as well. But the next Starmus will be next spring, next May, conveniently about a month after the big American eclipse, in Bratislava, Slovakia, which is just a hop, skip, and a jump from Vienna. So there are easy ways to get over to Vienna in Austria and get right over the border. And we hope that you will join us with Starmus. We have a lot of announcements coming on the Nobel Prize winners and the astronauts and the musicians and rock and rollers and everyone else who will be once again at Starmus next spring. Scott, you're going to throw a star party, I think, again for us.
Yeah, that would be a lot of fun. So,
and
the last one we did was really a blast.
It was something else. We had it at a 2,000-year-old temple last time. We have another amazing venue in mind this time, and we'll have an astro imaging school with Dr. Bakich and perhaps Scott involved with that as well.
Awesome.
So we're looking forward to another Starmus. This will be number 7. I will stop sharing and I will stop talking finally, Scott, now, and turn it back to you.
Okay, well, thank you very much, David. It was cool to get some insight into the Oppenheimer movie and also the Manhattan Project. So there's so many people that are still among us that have direct insight into that through their relatives and just stories similar to mine. So it's very cool. So anyhow, our next speaker is Don Knabb, and Don is with the Astronomical League, and we are very pleased to have the league with us every Global Star Party. So thanks for coming on, Don.
Sure. Let me share my screen. Should see a blue screen with the AL logo.
Yep.
Okay. So I'm going to talk a little bit. Now, I don't have a lot on light and color, but I do have talk about light years a little bit. So I guess that qualifies. So
Yeah, that'll qualify.
So I'll talk about the Night Sky Network and a presentation from the Night Sky Network. The Night Sky Network and the Astronomical League are really two organizations that they dovetail really well together. Before I get into that, let me mention that the next Astronomical League Live is up September 22nd. And there'll be more announcements about that. And Alcon next year is going to be in Kansas City. You don't know exactly when, probably in July, but it'll be in Kansas City. So the Night Sky Network is a wonderful organization. It's connected with JPL in California and also with the Astronomical Society of the Pacific. Full of some great people. And this is a snapshot from their website. And you can find local clubs and events anywhere you live in the country. There's a Night Sky planner that you can use and all kinds of outreach sources. I'm going to show you one of those this evening, just a quick look at one of the shorter ones. And there's so many things you can find on the Night Sky Network, and you can join for free, no cost at all. You might recognize this. This is from the Astronomical League. Again, as I said, they dovetail real closely. This is the Night Sky Guide that John Goss puts together every month. This is back from June, because I picked this from the a month or two ago. And talk about what the Night Sky Network is. So it's a nationwide coalition, amateur astronomy clubs that brings science, technology, and inspiration of NASA's missions to the public. And they share their time and telescopes, provide unique astronomy experiences at science museums, observatories, classrooms, and under the real night sky. So if you have a local club and you submit to your schedule of events, at the end of the year, if you do, I think just several of them, you get these really nice pins. Hard to see, I'm sure, but the pin from this last year was of the James Webb Telescope. And I don't know about other clubs, but the people in our club are really, really thrilled to get those pins. But here's from Alcon 23. There's someone you might recognize in the middle there. This is when Vivian White, who is one of the administrators of the Night Sky Network. Scott was very generous to donate a very high price Explorer Scientific eyepiece. Vivian won the door prize and immediately donated it to the National Observatory and Planetarium of Kosovo. So that's Vivian there. And there, you recognize that guy. In fact, there's a guy in the background too, I recognize. David Eicher is in the back. So, but yeah, Vivian is just one of the administrators and just a wonderful person all around. So this happened at Alcon, and beautiful eyepiece, certainly is. So in addition to the other things I mentioned, you also can get a monthly newsletter. And every month there is a webinar. In this case, back in July, it was on the Europa Clipper mission. And they offer lots of updates and lots of things. You can get a request a NASA speaker. They tell you how to do that. And if you have a club newsletter, they give you a What's Up This Month article you can put in your newsletter every month. So it's just a great resource. I want to make sure people are aware it's out there. It is if you have a local astronomy club, It's a great way to dovetail with the NSNs, we call them, the Night Sky Network, and get a lot of resources for your club. So one of the outreach resources, just for fun, I went on Galaxy and see what do we have in Galaxy, and you find this. All these things are totally free. Vivian confirmed they are not copyright protected. You can use these anywhere and everywhere. Okay, so this is one of the presentations. It's not very long. I'll just go through it fairly quickly, but it's about our place in the galaxy. Okay, and a lot of people, if you go to local star parties, a lot of people have this hard to grasp the Milky Way, how big it is. It's incredibly vast, and where are we? So this is a little presentation you can give at a library, to the Cub Scouts, the Girl Scouts, to a high school or elementary school class. But a lot of people don't understand the difference between the solar system, galaxy, and universe. A lot of people think that the stars they see are sprinkled among the planets. So here we have the solar system, the galaxy, and the universe. And it's nice to explain that solar system is in the galaxy and the galaxy is in the universe. So here's our solar system. And where is our solar system in this galaxy? It's right about there. We're in the outskirts. In the summertime, we can look in and see the center of the galaxy. In the wintertime, we look out and see more of the open reaches of the universe. How big is it? So light years. How far would light travel in a year? Well, it would take 100,000 years for light to go across our galaxy. What's that number mean? I don't have any gut feeling for that. So how can you explain to people what 100,000 light years is? Well, if we make this scale, if we say take a quarter, about an inch, size of a quarter, and let that be from the sun to Pluto, okay? From the sun to Pluto, that's 5.5 light hours from sun to Pluto. So think about, keep the idea of a quarter in your mind. That's the size of our entire solar system. So on that scale, a mile is 40 light years. 2,500 miles represents 100,000 light years. And as we saw above, 100,000 light years is the size of our galaxy. Interesting, and on this scale, the sun is 30 times smaller than a grain of sand, and the Earth is microscopic. So what do we know that's 2,500 miles in size? Well, the continent North America, something everyone's familiar with. So we can overlay with this scale of a quarter being the size of our solar system, we can overlay the galaxy on North America. So gives people an idea of how big this thing is when you think of a quarter of the size of our solar system. So how thick is our galaxy? Okay, it's about 1,000 light years. So 100,000 and 1,000. So at 2,500 miles, it's 100,000 light years, the size of our continent. 25 miles represents 1,000 light years. So it's a very, very thin galaxy, like most galaxies. Maybe it's like as thin as like a CD. When we used to have CDs instead of everything being online. So how can we envision 200 billion stars? That's how many stars we have in our galaxy. How can we envision that? So we take a football field and we get a bunch of bird seed, millet, little bird seed, and we fill it 4 feet deep. And that's about 200 billion stars. If each one of those bird seeds represents a star. Then you have to take them, you have to spread them over the entire continent 25 miles deep. So you're spreading them out, and again, it shows that space is what? Space is mostly space, okay? 2,500 miles wide, 25 miles deep, and only 200 billion, only a football field up to 4 feet deep of birdseed. So again, space is exactly that, mostly space. Again, that's a totally free, available to anybody presentation you can get from the NASA Night Sky Network, the great folks to work with. And I just want to make sure everyone's aware that they are out there.
Great, thank you so much. Thank you. So I noticed that the Astronomical League has a new website too. So
yes, we do.
Updated,
it's coming up.
New features that we should be aware of.
Well, it's not all up yet. Okay.
Okay.
It's at the old address, and like there's no information on the regions yet. So they got the basic framework up, and that right now is going to grow over the next months and years. So, but it is a much more beautiful site than the previous one. So, yeah, I forget the address right now. Astroleague.org.
Astroleague.org. Yeah, that's right.
So it's
So
worth looking at. It's a beautiful site now.
That's right. And if you don't already belong to the Astronomical League, you can certainly join a league club. You can go on their website and see a list of clubs. You can, if you live somewhere in the world where there is no Astronomical League club, then you can join as a member at large. And they have so much to offer with over 80 observing programs, scores of award programs that you can get involved with or you can nominate people for. And of course, they have the annual Astronomical League Conference, which is just a great showcase of astronomers and speakers and everything that the Astronomical League is. So you'll see me there for sure, along with lots of your friends here from Global Star Party. So anyways, Don, thank you so much for coming on. And again, thank you to everyone at the Astronomical League. Yeah. Okay, our next speaker is giving part 2 of his talk on dark matter. It's this great young man, León García, who was tied for first place for the National Young Astronomers Award that is given out by the Astronomical League, and I'm proud to say that we are a supporter of that program. León is coming in to you via Zoom from, I think, his home. So, León, thanks for coming on to Global Star Party again.
Well, thank you so much for having me on again to finish off what we started, and hopefully the first or second of many great presentations to come.
You're always welcome here. That's right. So thank you.
Yeah, I'm going to share my screen.
Okay. You are muted, León. There you go. You're muted again. Okay.
All right. So now everybody can see my title slide, right?
Yes.
With the 3 halo. Fantastic. All right. Well, this is just the second half of my presentation about dark matter that I started off last week. I'm going to get into a little bit more of what I did, but I am going to give a little bit of background and summary the first couple slides so that people aren't completely lost by what I'm saying. I'd like to start off by saying dark matter is one of these really important things in the universe that we don't know a lot about. It makes up 80 to 85% of the universe's mass. And this is important because it doesn't interact with electromagnetic fields. So we have no way to actually look at it directly. The way that we know about dark matter is from its interactions with things that we can see, like galaxies, stars, clusters, and gas clouds. And there's some major areas where we see dark matter having a massive effect in shaping kind of the evolution of the entire universe and of constituent structures within it. We see it contributing to gravitational lensing or magnifying light sources based on the amount of mass that the light has to travel around. We see that there is way too much mass being magnified to explain the amount of light that it emits. We see galaxies that are rotating too fast, too far out to be explained by traditional models of Newtonian mechanics. We see structures in the early universe forming out of completely undifferentiated soup or bubbles emerging, and that is primordial gas clouds. We see galaxies colliding that are orbiting one another too fast, and where we don't see light emitting mass, we do see gravitational lensing, which doesn't make any sense unless there's mass that we can't see. And finally, we aren't taking into account dark matter in the cosmic microwave background unless we look at like previous simulations of the cosmic microwave background, taking into account different amounts of dark matter. And we've arrived at the 80% figure from there. And the cosmic microwave background is basically just the leftover radiation from the Big Bang. And we kind of believe that dark matter is more or less cold, so it's not traveling at relativistic speeds, judging by the relative temperatures of various areas of the cosmic microwave background, which is a fascinating research area in and of itself, but not really the focus of this presentation. We have a lot of theories for what dark matter could be because we honestly don't know a lot about it. We know its effects, but we don't know what it is. So I'm currently exploring a theory that proposes that it's made out of this really, really light particle called an axion-like scalar boson, or a tiny particle that's 1/10 billionth the mass of an electron. This particular way of looking at dark matter is both really interesting and it's come to closer to solving a lot of problems with other dark matter models. For instance, when we applied this model to the Milky Way, the model that I'm using in my project, we've determined that it's come a lot closer to forming the right amount of dwarf galaxies that we can observe. Other models are forming upwards of 300 subhalos, or tiny little areas of dark matter that could host dwarf galaxies. Whereas the ultralight simulations are creating on the order of 25 to 27, which is much closer to the number that we see in reality. And other models are approaching infinite densities in their cores, meaning that they're predicting that dark matter is infinitely dense at the cores of galaxies. Whereas when we observe dark matter and its effects on rotation curves, we see that the actual likely core of dark matter in a galaxy or its halo is more of a flattened profile, which is much closer to what ultralight dark matter predicts. So what I did in this project is I applied this really promising theory of dark matter to four circumstances where it's played a super large role in shaping the universe at so-called cosmological transition points, or when the universe has been changing. Before I get into the rest of the presentation, I should clarify a dark matter halo is not a halo in the traditional sense, like an angelic halo. It's a spherical ball of dark matter that extends far beyond the reaches of your traditional galaxy. And it provides the gravitational pressure that that galaxy needs to form and rotate at the speeds that it rotates and form the structures that it needs to form. And without dark matter, we would not be here and I would not exist to give this presentation. And I guess I'm going to get into a little bit more depth on what this model is, but there's no need to understand completely everything that I'm saying in the next couple slides. So don't feel bad if you get lost by the wordiness of what I'm saying here. So I'm using this thing called a soliton, or a wave with a singular crest. It's a wave that has one peak, and it kind of represents an area where there's more gravity. So these tiny little particles, these axion-like scalar bosons, cluster together on a galactic scale to form areas that have enough gravitational potential to move galaxies. So these tiny little things are having such a large effect when you put a ton of them together. And so this is showing what the soliton looks like. This is an area with more gravity, and then this purple area is an area with less gravity. And although this presentation is about dark matter, this is a relatively colorful presentation, which is a good way of looking at how dark matter behaves. This particular soliton is about the mass and size of a dwarf galaxy, so I need a lot of these to actually simulate what a dark matter halo looks like on a really large scale. And I used this package that's already been developed for me by research, or not for me, but for anybody who wants to download it on their computer, by researchers in New Zealand at University of Auckland to simulate these halos. And it uses these waveforms to do that. And unfortunately, I had to learn a lot of pretty nasty math to do this project, or at least develop some sort of a conceptual understanding of it. And basically what I did is I solved this fundamental system of equations in quantum mechanics, the Schrödinger-Poisson system, using a particular type of numerical integration that is really nice with computers, or computers like to do lots of little tiny repetitive tasks over and over again. And so that's how it is able to turn this into this over here. So this is a graph of kind of what the gravitational potential or the gravity looks like from one of these solitons if you were to look at it from the side and slice it in half. And so this blue area is the gravity, and it's approaching this kind of flattened halo core that you want from observing galaxies. And you wouldn't want to just have these solitons sitting and not interacting with one another. So the way that you can get them to both move and be governed by the laws of wave mechanics is by using these things called Fourier transforms, which I use the package PyFFTW, or Pi Fastest Fourier Transform in the West, which is kind of a funny name. But these fast Fourier transforms to move these waves around to get them to interact with each other to simulate how a galaxy behaves. So that was a little bit of a mouthful, but this is what a simulation looks like. This one is not a realistic simulation. You see 8 dwarf galaxy-sized halos perfectly symmetrical and colliding with one another around a central mass. This is illustrating this property of quantum mechanics known as interference, or the wave-particle duality, where on very small scales, you can't tell if a particle is a wave or a physical particle. And so when you're obeying the laws of waves, you have wave interference, or constructive and destructive interference. And when you take a lot of really small particles that behave like waves on a large scale and collide them with one another, this illustrates a process that we see on a small scale, and it creates these really intricate interference patterns, which are governed by this wave function psi, which was in the last slide. But if you're really into researching wave functions, this is another way to approach it, is by looking at how this function can govern waves in different circumstances. So this would be a great springboard for future research. But this is the beginning of the simulation. It goes to the right, and then you jump down here and continue. This particular simulation's over 10 million years. And this is the format that I present my simulations in both my research paper and this presentation. And on to talk about one of the more realistic simulations that I did. Just a little bit of background on how the universe kind of changes over cosmic time is that smaller galaxies collide with other small galaxies to create larger ones, kind of like a survival of the fittest, if you will, where after these small galaxies collide and merge, they form larger late-stage spiral galaxies like the Milky Way and Andromeda. And the way that they do this is they collide and then they accrete matter in these accretion disks, which are basically a nice way to, or the lowest potential energy state for large amounts of mass that are rotating is by creating these disks that then create these large scale structures. So what I wanted to know is if dark matter, independently of any of my influence, would create these structures on its own if I just had random halos around a central mass. And that would tell us a lot about if dark matter itself was able to form these structures independent of any like baryonic mass, then that would provide more evidence in favor of this theory of dark matter, which currently hasn't been proved or disproved. And so that's what I did. I arranged 41 of these solitons around the central mass and basically just let them do their thing. And when they did their thing, they over millions of years, they were able to develop complex patterns and structures that are similar to what we would see in a late stage collisional spiral galaxy, which is really great for this particular theory of dark matter, because it shows that this theory, out of complete randomness, is able to form emergent structures. And another reason why this particular simulation is kind of important is because it hasn't been exclusively looked at the accretion patterns or the accretion disks of galaxies from a dark matter standpoint. In the literature that I've seen, more often than not, you have just an exclusively luminous mass, or mass that we kind of know how it behaves, circling a large central mass, which is dark matter added in as a constant. But dark matter is anything but constant. It's this own dynamic thing that should be simulated either on its own, which is what I did, or alongside visible mass in a more nuanced way. And so this particular simulation is important because accretion is a major turning point in cosmological development, and there hadn't been a generalized simulation, meaning I ran a bunch of these random simulations, and it was able to form structure. And so even if this theory was completely wrong, this methodology could be implemented by dark matter models in the future that are not ultralight dark matter. There's some other theory for what dark matter could be. And we learn that structure will form, even if it's not exactly the same structure that we want, out of complete disarray. And so that was one of the big takeaways from this research. Another thing that I did, or another simulation that I ran, was using prior simulations of very important galaxy clusters that have been extensively studied by other dark matter models, and applying this model to it because it hasn't been applied to it before. So the bullet cluster is one particularly strong example in favor of dark matter, where we see microlensing events in the blue, where there is no visible mass. And so that provides strong evidence for dark matter, and that's why a lot of previous research has been applying their own models to this particular event. And so I used previous inputs to kind of simulate this particular cluster of colliding galaxies, and was able to get a very favorable result just using those inputs. And it agreed with the observations of these halos in this actual galaxy cluster. So another application that I had using inputs from actual data in previous papers was the Coma cluster, the first evidence for dark matter that was discovered in 1933, where the galaxies in the Coma cluster were orbiting one another way too fast to be explained by their luminous mass. And when I ran the simulation using inputs from a prior study, I was able to get even closer to the number of desired subhalos, or these smaller dwarf galaxy-sized halos, produced in the final slide of this of the simulation than previous models were. So this is, again, providing really strong evidence for this particular dark matter model's ability to explain what we see is going on in real life. And these collisional simulations are important because, again, the universe is at a cosmological turning point where we are physically seeing galaxies collide with one another and developing the universe in over cosmic time. And so what we see is that we can use real data to input into dark matter models, which are purely theoretical. And so when we arrive at a model that's better than previous ones at even in a limited sense, where this model was limited by the amount of halos that I could simulate, other older models were not getting as close to the number of desired subhalos that we predict from looking at these things in electromagnetic wavelengths. And my final simulation was about the early universe. Out of this primordial soup, immediately after the Big Bang, there was completely nothing differentiating structure. So what that means is that there wasn't anything, there was a lot of stuff going on in the early universe. It was rapidly expanding, but there wasn't anything being differentiated out of the soup. There weren't bubbles emerging. And so what I was able to do was simulate under a very limited circumstance, not accounting for the inflation in the early universe, how a completely random arrangement of solitons or dark matter in the early universe, because many scientists believe that dark matter formed very early on in the universe's development, how that could have contributed to forming structures. And so what I was able to see is, again, out of this completely random arrangement of solitons, which is very similar to the one that the simulation earlier that I did with the galaxy, except there's no central mass here binding it together, so completely devoid of structure. We see pockets that emerge out of this randomness that stay together for millions of years. And this means that there would be enough gravitational pressure to form these structures over time that eventually evolve into galaxies. So this is really important to understanding the early universe from a dark matter perspective. And these simulations are important because oftentimes when we simulate the early universe, we don't look at it exclusively from a dark matter perspective. We more look at an inflationary perspective. And so testing ultralight dark matter in this new setting provides more evidence in favor of this theory, because even though it was these were limited simulations by the number of solitons that I was able to simulate, it still provided strong evidence that there were structures that were able to form and stay together over long periods of time. So my conclusions from doing this research project over 8 months, the interference patterns from the test collision were intricate, and I don't have the mathematics knowledge to study those in detail, because that probably requires some graduate level mathematics, and I'm just going into my undergrad now. But again, I'm hoping that the paper that I wrote gained some recognition, and that again, the halos were forming structures on their own in both the primordial gas cloud simulation and the galactic halo accretion one. And finally, the coma and bullet cluster simulations were matching up really well with what observations were predicting. But I'd like to say that this entire project comes with the caveat that one major constraint was that my PC memory, or maybe the nature of the simulation, was arriving at a computational limit, which clocked me out at about 41 solitons. So I was only able to simulate 41 different solitonic halos. And I wasn't able to account for inflation effects in the early universe in my primordial gas cloud simulation. But all in all, I was able to simulate many things that I really wanted to at the start of this project, and I look forward to continuing this research in the future. So thank you so much for listening to me again, and I hope to talk to you all in the future with more updates.
Yeah, you can count on me asking you to participate. So. That's great. So, León, what is it that you are working on right now? I mean, you've completed this this project. What's on deck for you?
So right now I'm getting ready to go off to college, and then hopefully I can continue doing research there, and I'm hoping to pursue something more gravitationally wave oriented, or high energy astrophysics, not necessarily in the same vein as dark matter, but I would like to flesh out this project even more, because I was able to get some really interesting results from my simulations that I'd like to revisit, maybe even in a couple more years when I can come at it from a different angle.
Sure. Sure, that's great. Well, lots of appreciation from our audience on your presentation. So thanks very much, León. And
thank you. I'm glad that they enjoyed it. And thank you again for having me on.
Great. That's awesome. Thanks, man. Okay, so you can see why León was one of the first place winners of the National Young Astronomers Award. I'm sure that we'll see more great things from him in the future. Our next speaker is Maxi Falieres, and Maxi is here patiently waiting in the background with a beautiful nebula behind him. And it's all yours, Maxi, but your audio is, you are muted. Oh yeah, got to pull the microphone down. Still no audio.
Right now?
Right now, yes.
Yeah. My microphone was unplugged. I think my wife unplugged it, so I didn't realize that. So good night,
That makes it
everyone.
harder.
Yes. So it's good to be back. Well, nice presentation, Leon. You know, I wish I had your knowledge. You know, you're a very young man, and you have a life to study. So keep on it. Don't stop it. And the life will regress you. It will give you very good chances. Okay. So, well, thank you for inviting me again. I hope you're fine. What I'm going to show you is what I've been doing last weekend. I was practicing again, trying to capture Saturn, but also I tried to how to see the deep sky objects with the f6 200 millimeters. So I grab all outside. Let me share my screen first. Okay, do you see it?
Yep.
Great. So basically what I was trying to capture, it was, I don't remember if I downloaded the image, what doesn't matter. But basically, I want to, sorry, it was in this place. I was capturing, started before Saturn comes up. I was doing almost 70, no, yeah, or 60 pictures of this place. This is the Bug Nebula in the tail of Scorpio. This is a planetary nebula. It's a really good one to try to watch it through a telescope, but I always try to capture it. I remember Nico did it with his Dobson. So I try to give a chance with this new equipment, and I was capturing, I remember it was 30 seconds every single picture. The results was, well, this is the another what I'm going to show you. The result of the stacking was this. Basically, you can see all the field of view, and here's the planetary nebula when I stacked all the images. But I have to process this. When if you can see, it's kind of, it was a cloud or something, or smoke, but this is light pollution, so I have to put out the background and try to give some details. So what I got cropping this image was this. So it changed a lot. I think I lost a lot of information, or maybe I didn't stretch it pretty good, but anyway, I was really happy to capture the structures of this particular nebula, and here the core that's spreads out from both sides, the particles and the of this dying star, you know. You can see the explosion that occurred here. But of course, the field of stars is amazing, and I really like the colors that I get, even here in my city. So then I went to a Trifid Nebula, but I didn't stack it. But anyway, I want to show you only a 60 seconds exposure, and you can see the field of view that I got here. You know, this is 100% of the picture. You know, it's incredible. I well, when I think when I get the stacking and some kind of post processing here, for example, in this place, there's two like antennas, I think, but it's difficult to see
Very
it.
thin. Yes,
Mhm.
very thin.
So anyway, the structures of this dark nebulosity, the stars, and the shape was really good, and only 60 seconds. Of course, I have here, I didn't work with a comma corrector because I don't have it, and I don't know if exists a comma corrector for these tubes. So you can see here the the comma and in the corners. So, but in the center, what I was trying to capture was okay. So then I pointed my scope to Saturn, and I start to did some captures, some videos, seeing what I could get, refocusing and everything. So the result of that night was particularly this. You know, I
Wow.
I was really impressive of the result. I remember when I finished this, it was almost 5 a.m., maybe 6.
We're impressed too. We're impressed too. It's beautiful.
Hmm. So, and I think, I don't know if it's okay, but if you put it more, let me put it more here. Uh, you can see here it's like a white band.
Oh, like a storm or something.
Exactly, but I don't know. I didn't saw pictures from well, from this night, so I don't know if it is or not. But anyway, we are now for now able to see partial of the Cassini division, the lines of storm on the equator, but this is the northern pole, and the southern is coming to rising. So if we compare it from a picture from the last year, it's very different of the position in this case, because remember that Saturn has a different orbit around the sun, so it's a kind of inclinate. I think it's okay how I say it. So I was remember that I did a comparison of different years. So, for example, you can see here. Let me put it. This is more up. This was 2018. This was 2019, 2020,
Mm-hmm.
2021, last year, and a couple days. You can see how the rings change of position, and also the line of the equator. The first ones here are my first pictures that I took with my cell phone and simple equipment. But now I'm trying to focus to get more details on this case. So unfortunately, we don't have very good nights of seeing. The jet stream kills a lot of details. Well, then when I tried to capture Jupiter, it was impossible to see the details. It was
Hmm.
only, unfortunately, it was only some lines and a blur, a great red spot. No, uh, it doesn't worth it, because in my position, we will have it almost maximum 40 degrees. So at that altitude, the atmosphere will blur your image. So when you try to capture it or film or record it to get the best frames, uh, it doesn't work. So anyway, I think in a couple of years we're going to have it more above our head from here, and I hope those days come really fast. So, well, this was my presentation. I hope that you enjoyed it. My next work, I think, if the weather allow us, maybe this weekend we have a holiday, or from the pass away of José de San Martín. So a Memorial Day. So we have the Monday that we don't go to work. So I try to go to Alberti to do some deep sky object imaging. I will see if I could get some galaxies. If someone wants to ask me, or maybe tell me that or to capture some object that wants it, please write me to, and I will be very happy. And also for those who wants to see my pictures or wants to use my pictures, for example, I'm really happy to collaborate and give them, for example, to the Astronomical League if they want to maybe practice or something in or
cool.
processing. So I'm glad to share it. It doesn't no problem.
That's
for me.
wonderful. See, that is the epitome of what a great amateur astronomer is all about. They will share everything. And,
If NASA does it, why I will not? They give you the best pictures of the James Webb
that's true.
telescope, the Hubble telescope, and you can practice and with the Hubble palette and everything. But why I will not share it? Of course, my equipment. I spend money in my equipment, but because I want to capture it. But if you maybe process better or try to practice with something, I will glad it for that. So,
Okay.
well,
Wonderful.
I think it's all for tonight, Scott, and thank you everyone, and have a nice week.
Great. So I've just posted a link to Maxi's bio page on Explore Scientific. He is an Explorer Alliance ambassador. Thank you so much again, and I hope to see you again next week. Take care. Take care. Okay, our next speaker is Tom Field. Now, those of you that might have met Tom, he is probably the most enthusiastic ambassador I've ever met about analyzing spectra. Now, you might think that's a really dry kind of thing to do, but through spectra, you can see what's going on chemically with the celestial object that you're examining. You're able to measure distance and velocities and stuff like that. So, why wouldn't you try it? Now, one reason why you might not try it is that you think that this is really hard to do. But in this presentation by Tom Field, you're going to find out how easy it is to do and how inexpensive it is as well. So I'm going to turn this on now. And Tom, if you're watching, thank you for putting this presentation together.
Hi, my name's Tom Field, and I was a contributing editor at Sky and Telescope magazine for about 10 years. I'm a software developer and an admirer of the skies. We're going to talk today about how we know so much about the stars using spectroscopy. We'll start out with this gorgeous, iconic image. These are shock waves of enormous power, of course, creating new stars. When I see this image, I always ask myself, what about all these other stars? Where are they in their life cycles, and how do we know? And that's what I found spectroscopy helped us understand. So the history of humanity and learning about stars is centuries of men and women doing science, many times going down dead ends. Now, to be honest, if again, I was in this picture, I would be a little dot way out on the horizon out here. But I wanted a front row seat, and I found that what I'm going to talk about today helped me understand what the giants did over the last several centuries. So my process and my learning curve was a little bit disappointing at first. I read all sorts of online sources and texts and magazines, but I found that a lot of it just didn't come together, and I didn't remember a lot of it. I don't have a degree in astrophysics. I'm not a scientist. I just wanted to understand more about the beautiful skies that we observe. And I wanted, when I read things in magazines, to understand a little more about what they were talking about. I found out that spectroscopy allowed me to do that. So I'm going to show just 3 quick examples today in the Perseus star field. There's the star field, and what can we say about this? Well, as devil's advocate, I'd say this is a pretty boring star field, right? It's a bunch of dots. Maybe there's an asterism, doesn't seem to be any constellations. The one thing that's here is there's some stars of different colors, so maybe we could tell a little bit more about the temperature. But we're going to look here at just 3 of these stars in the time we've got available today to show you how we know so much more about them. Now, the first thing we do is in spectroscopy is we have to split that starlight into rainbows. So here are the same 3 stars. Now, this image was captured with just a DSLR. So let's take a quick aside here to look at this. It's just a standard everyday prism, and if I had a bright light and I shined it through, we'd get a rainbow, right? Standard stuff. But I didn't have enough duct tape to put this on my camera. So these days we don't have to. It's so big and clumsy. Now we can use just a little 1.25" grating like this one. It's called a star analyzer, and it sells for less than $200 and screws right onto your camera. And I want to demonstrate how it works here. So it's going to take a little bit of juggling. But here we've got a really bright light. And when I hold the grating up in front of the light, you can see that rainbow there. It's just the pieces of the rainbow because this is a pure gas. But that gives you the idea that this works just like a prism does. So we can split starlight and look at the spectra here on the screen. So let's start out with just this star here. There's its spectrum over here, and we can see what about it? Well, it's not continuous either. It has some little gaps in it, doesn't it? And those gaps are how we learn about the stars. Now, we're not going to get into a lot of the science today, but trust me, the science isn't hard. We don't have to drill down really deeply into quantum mechanics or anything like that. So just a quick overview, and that is each element, when we burn it, or when light passes through it, has its own fingerprint. So this hydrogen here, we can see that its lines here and here, what are called the bomber lines, are very different than the lines we see on helium. And that's all we have to know. Now, how are those lines created? Well, just really briefly, as electrons jump around in the Bohr model between orbitals, they give off or they absorb light. And that's all we need to know. If you want to know more, then you learn more. Once you have data like this, it gets more interesting and you end up learning more, as I found. But so, one more example of how these fingerprints work. This is actually a poster that we offer to teachers, 36 by 24 inch poster. And I just wanted to show you here that each element really does have a different fingerprint. Okay, with that in mind, let's go back to this image. This was done with just a DSLR. And the DSLR with a tracking mount with a star analyzer on the nosepiece. So these gaps here tell us that this is a type M star. Now, what does that mean? Now, there's lots of ways to talk about this, and I'm not going to spend a lot of time on this HR diagram, but I wanted you to see just really briefly, if you're not familiar with it, that we can classify stars by temperature. And a type M star is a cool star, and in this case, the star we're looking at, we know from its spectrum, is a supergiant. And there we can see it's just like Betelgeuse, for example. And we learn that from the spectrum. So what we're learning is how to navigate this map of star life cycles with data that we captured ourselves. Let's look at this second star here. This is called a BE star, and it doesn't have all those gaps. It's got one here, but it does have this bright spot here. What's going on with that spectrum? Well, this is the spectrum of, as I said, a BE star. So it's a B star in temperature, and that E stands for the emission from the dust in that circumstellar disk. And we're actually seeing that glowing dust right here, just with a backyard camera. By the way, spectroscopy is much less affected by urban light pollution. So this is the kind of thing we can do in the cities. We don't have to travel to some dark sky site and, capture hours worth of data. Just really short images because we're looking at really bright stars. Okay, so that's the BE star. Let's go back to our HR diagram, and we can see that B stars are over here. And so this BE star is going to be somewhere probably up in this area like Spica. By the way, I just wanted to point out another familiar star or two here. If you're not familiar with this diagram, there's our beloved Vega, for example. All right, so now we've seen two different regions in the HR diagram using data that we captured ourselves. Let's look at this third spectrum down here. This is called a Wolf-Rayet star, and look, it's got all of these bright spots. Not just the one that we saw up here, these bright emission lines. What's going on with the BE star? Or excuse me, with the Wolf-Rayet star? Well, these are late-stage stars that have blown off a lot of their outer shell. They have really intense stellar winds that broaden these lines so that we can see them. And again, we're not going to read all this, but this is the kind of thing that once we've captured the spectrum ourselves, makes for much more interesting reading. And the only thing I wanted to show you here was look how hot these stars can get. So on this scale down here, those stars are going to be, way over in this area. So, excuse me, we've navigated the HR diagram, as I mentioned, looking at 3 different star types. And this is the kind of thing that we can do as amateurs. So how do we do it? Well, we can capture spectra with almost any instrument. I mean, a standalone DSLR, as we just saw. It can be a telescope. This is what the Explore Scientific ED102, great telescope for this. Both of these would have to be on a tracking mount of some sort. And then how do we actually capture the spectra? Well, we use this star analyzer grating that I mentioned a few minutes ago. So let's start out here with the star analyzer. Just looking here with a standalone DSLR and this adapter that we make available, you can actually capture the spectra. You don't need a telescope at all. Or if you've got a FITS camera, you can put the grating on your FITS camera. If you want to put your DSLR on a telescope, we've got a way to do that on the T-ring. You can use a video camera, which makes for just fantastic outreach and education. To show a live spectrum flickering on the screen, it's really captivating and people love to see it. We can also, of course, put the star analyzer grating inside a filter wheel. So there's lots of ways to set these things up, and there's lots more information on our site. How do we capture the spectra then? Well, over here is an image from our telescope. There's the star, and maybe you can see on your monitor there's a gap right there. But we want to do science here. Maybes aren't enough, right? So this is the software I wrote. It's called RSpec. I don't know why I'm circling it up there when I could circle it down here where you could read it. So the software looks at the region between the orange lines that we can drag around any star, and it just sums up the data and gives us an intensity plot. So this dip in the spectrum here, sort of in the blue-green, is that gap I was pointing to here. There's lots of other absorption lines that we can see in the data once we graph it. So this graph makes things much, much clearer. And then once we have this graph, then we can use tools that are built into the software and other reference works to figure out what type of star it is. In this case, this is Vega, and those are the hydrogen bomber lines that we captured. You can capture these, as I said, with videos, which means we're just talking about exposures that are less than a second. So, I'm often frustrated when I read the magazines. I see these gorgeous images of galaxies, and then I read the fine print, and they say it's 10 or 15 hours of integration time on some mountaintop dark sky site. I live in Seattle. We have a lot of rain. We have very short nights in the summer. I'm a terrible imager, really, and I don't have the patience or the knowledge or the equipment to do that kind of high-end stuff. But this kind of stuff I can do, and I'm sure that you can too if you want to. So really, that's all I wanted to tell you today. A little bit about how we process spectra, the kinds of things we can learn from it. When we're looking at star fields like this one here, not only can we learn about the star forming regions, but we can also learn about the life cycles of all the stars in the field of view. It's a really exciting field. Our website has lots more information. There's a contact form there. You can communicate with me, look at the tutorial videos that are there. I hope this presentation has been helpful for you, and I really appreciate the opportunity to speak here today.
Well, that was a great presentation. And Tom, again, if you're watching, thank you very much for making this available. I'm going to keep that video for future presentations as well because it's so good. We are going to go from Tom Field all the way down to Buenos Aires, Argentina, where we will meet up with Cesar Brollo. Cesar, I suppose, is out there on his balcony once again. So here we are. And yes.
How are you?
Good.
Hi, everyone.
Yes,
Like
Cesar.
clear sky tonight. Is it clear?
Hello, Maxi. Hola, Maxi. Hi, Scott. Well, cloudy, of course. I had. Can you hear me?
Yes.
Yes.
But thinking in the possibility to have a lot of clouds in the sky here in Buenos Aires, I can show you my screen now, my live image for now for the which is pointing the telescope is pointing to nothing, but
nothing.
to nothing.
I thought that you were pointing to your neighbor on the building behind you, but well, great. Yeah, you're pointing to the clouds.
Sure. Some of the windows, but no. I don't like to have some problems, you know.
Yeah.
But we
Maybe you can talk
about
a little bit about your setup and
yes,
what you usually do.
I have a very small presentation and talk about optics. You know that I am optometrist.
Yes.
We can talk about the difference sensation about colors watching by your telescope, to the naked eye, and comparing the same image when you make a long exposure photography. Something that is more then for people that know more for me about astronomy is and something that I can't explain, but maybe about the colors. When you talk about how strong are the colors and the light and the bright in a nebula. If you go to the nebula, many people say the same for boreal auroras. That many people say, okay, I saw auroras and are not so bright and are not so brilliant, and the color is more a pale color. Many times talking with astronomers about the ionized gas of nebula, you know, you can have a very bright, talking about if you can go to the place. Of course that you lost a lot of light by the distance, because it's the square of the distance is totally comparing with the quantity of light, and it's not the same the light in a point or a small disk, like a planet, comparing with a big area, often in this case, gas of nebula. And of course that the level is not easy to say. If you are thinking of how real you can show a nebula about colors and light, if you make a 4 hours exposition for example, Lagoon Nebula, maybe you have a huge color, but if you go to the same place with your eyes, the question is, you can feel the same big, brilliant, and strong colors if you see the same at the with the distance that you compare with your telescope. Maybe for your telescope, you have, talking about, it's all about optics and about our sensation. Our normal field of view is 120 degrees, and our perception of and our attention is no more than a coin and 1 meter. In our brain, we assemble the image, the idea of the image, and the sensation between a picture, between sensation of the real, how bright is the nebulous in the place if you can go to the nebula. Well, you can compare something. Let me share a screen with a small presentation.
Okay.
You can see, well, not the presentation yet, but I have. Well, and we can talk about the perception of colors and bright. And many people ask this question about if the nebulas are so brilliant, or if you go to the outside or deep, if you go to the deep sky, and we can compare in our Earth, in our sky, night sky, when you go to the clear night in a rural area or mountain area without light pollution, we know that how we see the Milky Way. We cannot see the Milky Way like a picture of Adrian, or the colors that you can see. You can see the color of the for example, in summer we can see the cross, Southern Cross, but we can't see the color of the Eta Carina Nebula. We confuse normally the cluster and the Eta Carina Nebula. We know the position of that. Both are very big in the field of view. Small when we watch, maybe are, Carina Nebula maybe have 2 or 3 degrees, and the cluster that is near to Carina Nebula, it's similar, but we can see the color. When this is to the naked eye, and our normal view of the sky. It's the same for auroras or for many things. This is the typical thing that we watch when we watch the Lagoon Nebula in a medium-sized telescope. Maybe Scott, you can tell me that is your sensation. It's very difficult to say where and with which telescope you can have the same perception, but when you can see Lagoon Nebula, you have a very finely finely. Maybe if you have this sensation, you are lucky. You are in a deep sky, sorry, in a dark sky area. Is of course that when I put in my you know, for processing a picture to show something, it's impossible to have the same, because you have more perception of the stars, but in the real life, but you have a very sensation of the finely ghostly nebula, very what we call, when we sell a telescope for the customer are expecting this with the color and
right,
and
you see this brilliant,
yes,
amazing,
absolutely,
colorful image, right?
yes. But if you watch Lagoon Nebula, you can advise about this, you can not advise, you can see the difference about these shadows between, and it's very different when you have of course a very long exposure nebula, a picture of a nebula, and you have this. Fortunately, many people are coming to have some kind of possibilities to make long exposure astrophotography for the different objects in the sky, and they can receive the magic of to have colors in their nebulas and make something that is very using the word that John told me that last week, rewarding for them, and it is something that is a new age. It's all about why we can see the colors in the night. It's the same. We have conos and bastones, different cells, sensible cells in our retinas, and of course that all that about perception in the low light are black and white sensitive cells, and all for sharp and colors are sensitive with more light that they need, and this is why we can see a telescope color with of the nebula without make electronic CCD or reflex camera digital long exposure photography. Here you have about the colors. This is here how we see here is the Southern Cross. Here you have the carbon soap, and this is Eta Carina Nebula. And this picture is more near to the reality, where you don't have, you see the Eta Carina Nebula and this cluster like the same color, but you don't see the colors of the nebula, and to the naked eyes and with the telescope it's the same. This is how we need calibrate the color for the final image of a nebula using the Pletsolve software that give us the best choice of colors for a final image. This is a single shot that is very different to the final shot, the final result that you have when you process in a picture. Today, about the colors, people say, "What? This is not a real color." Of course, that it's very difficult to make a real color, but the software with calibrate colors, photometric calibrate colors that you have in many applications or software for processing image, give us the most realistic colors, because the colors have a number in astronomy that is the last that we listen about spectrometry, sorry. And we are going to have the most realistic colors of the nebulas and galaxies, because you have a number that give you a color. Is something that many people say, but maybe the difference is to say your red is the same that my red. This is a perception, maybe it's a neurological perception, but if we start to talk about our retina, we have the same kind of cells. It's very, how do you say? It's very not easy, very far away of the reality that we are watching different colors.
Yes.
Of course, that exists. We have a lot of tests for blind colors, and it's something that I work with this. But when we make this kind of test, we receive fastly that say, okay, you have a blind color. Without this, we are talking, and the sensation of the colors are the same. Well, here you have the comparison between a single shot with a color of that received my reflex camera and the calibrated color in the final image. And this is maybe the most finely here and more strong the stars, of course, but when you see Eta Carina, you don't see more than this area and maybe some filaments or something like a clouds in this area, and you compare the image. If you use a big telescope, we was talking about the sensation to see something yellow or gold watching this nebula, but over 16 millimeter Dobson telescope in a very dark sky areas. It's very the first colors that normally you receive in your retina is between the yellow and green colors, and it's not easy to this is maybe where you can have difference about the sensibility, how your retina is sensitive, and how much you can open your iris. And this is very interesting, the perception in our eyes, but maybe technically the colors that we are talking in a normal, without, of course, this is like blind colors, do have the same perception. Here, I remember that I told about this cluster like Southern Pleiades, but it's not a Southern Pleiades. It's very near to the, I remember that it's a 3335, the cluster. And here you have a lot of different colors of stars. Actually, maybe my simulation of how you can see the cluster. Maybe this is in the city with a cloudy night like now, and you have a very without bright stars. But you can see, for example, this like you can compare when you have a pointly stars. It's very easy to compare bright and color. Only we mostly of the times we see without color the nebulas and galaxies, but mostly of the time we watch with colors the stars, and we can compare. And this is all that we can make with our eyes, comparing with long exposure photography. let me see. My idea tonight was, but of course that we can make the same the next week. We can point in a live image. Let me see if I have a little less of clouds. If we can see some in live image, something. Let me see. No, nothing. Let me check.
Nothing.
No. Maybe I can move the. I can show you maybe in this area.
Okay.
We can try.
Yep, go for it, Cesar. I am going to be ready to present next, but I'm booting up the main computer so that I can use more images in my presentation next. And I hope
your
the
presentation
invitation
have a lot of color every time.
Yes, and you have to be careful sometimes because if you overdo the color, I'll talk about it in my presentation a little bit about when we listened to one of the folks who is contracted from NASA to process JWST images. I think that'll be interesting for the folks to know. They don't do much different than regular astrophotographers with PixInsight, Photoshop. They use some of the same tools. But
yes.
Finish what you're doing, Cesar. I'll save that for the next when I get back on in the next few minutes.
Of course, that I don't have more for my presentation. Only 1 second to show if we have something in the field of view of the telescope, but only I can share screen few seconds.
Okay.
Go for it.
Typically, we say nothing. You can see my Nina screen.
Yes.
We can move a little a telescope.
I see some faint stars.
Maybe it's an imagination. Let me check
Is it out of focus?
No. Because it's actually we have. Let me check. We can try if in the area of Beta Crucis we can see nothing. No, because it's maybe if I have something more clear in stop sharing. Maybe if I have a part of the sky little clear, I advise you, Scott,
sure.
Only few seconds later. No, for the end of the
maybe towards the end
the
of
global
the program.
safari, of course.
Okay.
Yes.
Okay, you just let me know.
But we have a huge layer of clouds, and of course that I send you the message if I have real clear sky. But okay. This was my presentation, was to talk about light and colors, maybe more in the idea of optometrists and how.
Yeah, that's a big argument. What is the real color of something? And
yes.
because it is astronomers often assign a color to a part of the light to identify a certain region. So
yes.
That's right.
All that the tool that we have is the number of the sequence of the spectrum.
Exactly. Right.
Maybe you can say okay, do you have a hydrogen or oxygen, and you can say, or you can receive the idea of calibrate a more real color. But my idea sometimes is when, for example, when I say many auroras of Adrian Brollo, if you go to the place to the auroras, if you see so green color and so brilliant. And if you go, or that is a hypothetical, if you can go to the nebulas, you see the nebula so bright, so strong, or you can see the color, of course, but more in a more soft, bright,
More diffuse. Yes.
more diffuse. I don't know. It's a question. I don't know. How think the audience about this?
Well, that would be a good question to ask Michael Carroll, who will be coming on here in a little
Yes,
bit.
yes. I think that is a question for him.
Great. Thank you so much, Cesar. We will see you next time. Take care.
Thank you very much, Scott. Thank you to the audience.
All right. Thank you, Cesar.
Okay. All right. So, yeah, we have Adrian Bradley on. Adrian is his program of Chasing Dark Skies is, you know, this guy is on a mission of getting the best night sky shots that he can possibly get, and he often takes images that are totally breathtaking. So, thanks for coming on to Global Star Party, Adrian.
Thank you for having me, Scott. I came in basically just in time. And Cesar, I'm glad you actually ran a little over time because it gave me time to get onto the main computer. I am going to try and do a shorter presentation because I'm interested in hearing Michael Carroll as well. I promised that I would talk a little bit as I'm sharing my screen and showing some of my earlier work. There's two themes I wanted to do, and that's talk about Perseids. We just had the peak of the Perseids, and I want to talk a little bit about, you know, where to see them and or where you went to see them. And if you didn't see many meteors, I plan to tell you why. First, I wanted to reiterate a little note. Those of you who may not realize that those who process images, and they do so on a professional level, the JWST images, they work with scientists and they work with things like Photoshop, Lightroom, PixInsight. There are a couple of other astro images, same as the astrophotographers like Cesar, Maxi, and I'm thinking Jason Gwinzel, who comes on Global Star Party. All the astrophotographers that we've had and the astrophotographers contracted by NASA to produce JWST images from the data that that's made available to them use very similar processes. The main difference is that while they know that these things will be beautiful, the scientists working with them want to see certain elements. And with my own photography, I began to look at it in a similar way. I want to see certain elements, and those elements become more important because they tell the story. Here's a Perseid that I shot some years ago. I think it's 2018. If I go to it's 2019. Okay. In 2019, learning Milky Way photography, you know, having an older camera, but I caught this Perseid. It, to this day, probably the brightest meteor that I've caught. And I never saw this meteor with my own eyes. I heard about it. Someone else near me said, "Hey, did you see it?" And I said, "What meteor?" And my camera clicked off, and I looked at the image and saw, oh wow, I've got a bright meteor in my shot. And it was I think it ended up in a calendar at my job, working at Comerica Bank. Other times meteors happen, and why I'm calling this a meteor is the taper. It goes from dim to bright, and if it's a solid sweep like this, you know, this could very well be a firefly flying near and made that trail. These other specks are fireflies, and there's there's a streak of a car that was going along the road, and this streak was a meteor. I had looked up and said, I'd love to see a meteor. We had a astronomer was that passed away, whether or not, there's things of a soul. Did he have a capacity to send me a meteor? But I kind of said, hey, John, you need to send me a meteor. And with the Perseids, they come often enough that it all of a sudden meteors can appear, and you don't know if it was a metaphysical thing or was it a coincidence. Either way, this meteor appeared. I never saw it, but turning around, I saw a bright fireball go across the sky. I was the only one at the park, and I just sat there and appreciated the fact that I saw it. Now, when you're in any skies, this is the same location with me trying to reprocess an image. And look, there's two meteors. Was it the Perseids? This was August 2020. May have been. It was the Perseids between July and August. So these very well two Perseids that happened to show up during this 1 minute exposure. So getting meteors, faint meteors, is not too tough to do. It's whether or not you get a bright fireball. So I've yet to get super bright fireballs. Here you have a satellite. Solid. These things are solid, and they appear to be about the same length. Then you've got more streaks that are solid that appear to be about the same length. And could they have been meteors? Well, maybe, but anytime you see these streaks, they tend to be around, if they're around the same length, they tend to be satellites. So that brings me to Perseids from a couple years ago. And yes, these are over the years, I've taken a number of images. If you've been to Global Star Party, you've seen a lot of these images. This was from a couple years ago. Now, David, our esteemed David Levy, looked at this and said, "Are you sure that's a meteor?" And I understand, because it certainly looks very solid. But if you look close, there's a point where this part of this meteor. Now, I saw this as it came overhead towards this part of the sky. And if you look carefully, you notice there's a bright spot in the middle. Meteors disintegrate, and then they tail off as they entered Earth's atmosphere. And so you can see it's, as the exposure ends, it's beginning to tail off. So that's one telltale sign of a meteor, is that you saw it and you know that your camera was aimed towards it. Now, in this location, we saw something like, for every minute, we saw no fewer than 6 meteors streak across the sky, and sometimes even more. Darker locations present more meteors, just the simple fact, and this is during the Perseids a couple years ago. This was Perseids of 2021. There's more opportunity to see meteors. Now, was it a satellite or a meteor? There's lots of streaks in here, and you have to examine the streaks. Because this streak is fairly solid, it could be either one. There are a lot of satellites, and those bright satellites will show up, and you might not be sure. This faint thing could be a satellite, or it could have been a meteor. So there's always a streak in your photo. It just depends. And here you have a telltale sign of a meteor, if it'll come in, because you've got faint, bright, and then beginning to get faint again. That's your telltale sign that you caught an actual meteor and not a satellite, is the way it looks. Or like this one looks more like a satellite. but this is one that I saw visually. As I was taking this image, I saw this meteor. Now, these are the type of images that some part of it is composition, part of it is luck. It happens to connect these two trees. That it's nice, but and I purposely sat in a location where Vega as it's pronounced, sat right here, and with haze showing up in this night sky, and this is the Cygnus Rift. I believe one of these is considered the northern coal sack. I believe this may be it, northern coal sack. So everything just kind of happens to come together on some of these shots at night. So you just have to keep shooting. You have to keep imaging to see what kind of things may happen. Distant thunderstorm, and I don't think this was during any particular shower. It does say August 28th. So could have been a remnant of the Perseids, or it could have been, this is north. This is due north, so it could have been a different meteor shower, but you definitely see the telltale signs of a meteor, and we call it a lightning bolt. So there's a couple of things that appear in images at the same time. I'm looking to capture more things like this. I like the idea of capturing distant thunderheads, and it's something I don't often get to do. And so whenever night sky photography, sometimes there are different things that you can do to continue getting inspired to try and go out there. It doesn't always have to be about the Milky Way. It can be about, a thunderhead in the distance and a meteor, and see if you can catch the two at the same time. Of course, there's a plane as well. Streaks, not meteors. And so finally, how about 2023? Well, we're going to go all the way down and skip through all these things and, thunderheads. And we're going to come. This is a great place to visit in Michigan, this lighthouse. We're going to come down to the smoke moon, and the last two images I will share for my presentation tonight. You are free to debate whether this is a meteor or not. Notice the detail in the Milky Way compared to that first shot, and how the composite is put together such that it looks a little more natural. Mm-hmm. What you're trying to do, not necessarily for, accolades, but I always try and reproduce what it is I see. And there happen to be people here. And so I left their shadows in as they were moving. And it, kind of a composition choice. You have two people here. Is very likely a meteor, but could it be a satellite? It certainly could be, especially when you look at the fact that you don't see a real explosion point here. So more likely a satellite than a meteor. And then finally, this image. I like this image just for the pure fact that a lot of times when we image, we focus so much on the night sky, and you got what I believe is a combination of streaks from meteors. This one definitely, because you can see the telltale faint to bright, and there's double cluster right there. And these very likely meteors as well, or it's pretty well, there's a little bit of a taper there, so it could have been a meteor that was there and I caught the tail end of it. This one, it all depends on, if it's a meteor, it depends on when it shows up. But just like Marcelo's, who will be coming up next, I believe, Scott, we like to share when it's an outreach event and people are laying on their backs looking at meteors. It tells such a wonderful story.
Yes.
And then, we have this dish, which is not in use, but it's a radio dish that the University of Michigan did use at some point. People may be fuzzy, but you can tell they're all looking up.
Oh, yeah.
And the sky is this part of the Milky Way bright? No, but you see a sky full of stars. I dare you to be able to make out the Big Dipper in this, and good luck finding the Little Dipper. I actually could not trace out the stars of the Little Dipper, and it just makes you wonder what it would be. This place it's not very bright, and you see these light domes, but all of these stars are real and they exist, and
Sure.
it makes you wonder, if you go somewhere dark enough, you'll look in the sky and see this with your own eyes.
Oh,
And
yeah.
that's why I continue to chase dark skies, because I like seeing this naked eye. It's great to take a picture of it, but you go somewhere that's even darker, it blows your mind. And if you haven't been to a place that's super dark like that, I highly recommend go, even if it's for a couple of if it's for a day or so, if it's an overnight trip, and go enjoy the night sky. And hopefully you saw some Perseids. A little footnote, the Perseids I caught in that picture, the crowd didn't see those, but they saw some big fireballs that I did not get a chance to capture. So with that, Scott, I am turning it over to you.
Thanks, Adrian.
Hopefully...
Thank you. Thanks for coming on to Global Star Party again. We'll hope to see you next week. So
yes, same here. I will be working on my schedule so we can make that happen.
Great. That's good.
All right.
Thanks so much, man. Okay. Up next, we're going down to Brazil to visit with Marcelo Souza. Marcelo is the editor of Skies Up magazine. He also runs the Astronomy Club, or the Louis Cruels Astronomical Club down there in Brazil, and they are movers and shakers in astronomy outreach in the area. Marcelo also is instrumental, and his team were instrumental in creating the first international dark sky site in Brazil, in fact in the southern in South America. And so it's a pleasure to have Marcelo on our program. And I'll add, he doesn't often throw that out there, but he is a cosmologist. He's an astrophysicist. He teaches physics, and it's a real honor and pleasure to have him here. Thanks for coming on, Marcelo.
Hi, Scott. Thank you very much for the invitation. For your kind words. Thank you very much for the invitation. I will share my screen here. I will show some new events that we organized here. Let me see if my computer is not so, but it's working. This is our Astronomy Club. Here is our last event that we launched a new nucleus of our Astronomy Club in another city near us. Now we have groups in 10 different cities here. Our club is growing here in Brazil.
Yes.
And here are the two members of our club, me and in the left part of the image, you have Robson also, and the others are members of the city. And we organize these events. This is the place that will be located. Our nucleus there is a public school. Has a big auditorium there. And this was the first event that we organized there. And after the celebration, we organized a the observation of the sun with the glasses and with a special the Coronado telescope. And we have the participation of a lot of people. Most of them are students. And also have the opportunity to show the sun for the kids. Then this is something that we are doing now in this period because we are organizing the observation of the partial eclipse of the sun that will be partial here in October 14 for us here.
Great.
And we are visiting schools and we received many glasses from Stephen Hamilton to give to the pub. And we are now visiting schools to talk about that they need to need care, to look to the sun, and we are giving to them the glasses, and they also are looking using our telescope here. And all the events have many people participating. Now we have nucleus in different cities. Then we are organizing at least the observation of the partial solar eclipse in 20 different cities near us here. And we are planning to reach at least 3.5 million people. 3.5 million people. This was an image from the last event that's organized at night. I'm showing this image I showed last week because now we are beginning a new project that in English we call Count the History of Stars. We are inviting the students to go with us to dark place, and from there we are asking them to count the stars, as you have the projects also from many different places. You have the Globe at Night and different projects that you are going to use, and we ask the students to write, to create a history for the star that they see, and then they count the history of these stars. And we will begin next week this project. We also have a partnership with this protected area, protected forest near the ocean, and we organize events there. We organize this week, August 17th, and also next week event for the students there. Now I'll talk about the lights. A little about the lights. I don't know if someone already talked about what I will say now, but for me, a famous experiment that I ever talk with my students here when I talk about optics in my course is the experiment made by Isaac Newton. That was one of the wonderful experiments of the history of physics. When he was in a farm, he stayed 2 years in a farm because of a pandemic, like what happened with us here. And during this period that he was in a farm, he developed their theories there. And one of the fantastic experiments was this experiment using a prism. He looked for the dispersion of the light of the sun when cross for he has a protection in his window, a hole in this protection. Then he passed the light in a prism, and then he saw the spectra, color spectra. And then what he did that is fantastic. This other people did before him, or in the same period of him. But what he did this, and he put in a screen the spectra, the rainbow here, and then he make a hole in one of the colors, and after this he put another prism. Then he showed that the dispersion of light only happened with the white light. This didn't happen with one color of the light only. What happens is only that change the direction of the light. Then this, in the period that he did this, is something fantastic, because many people imagine that something happened in the prism that can change the nature of the light, something like this. And then he showed that this was a dispersion of the white light that's composed from different wavelengths. And what happens when is in the prism, because they have different paths, because they have different velocities for each wavelength in the glass. And the form of the prism that help us to see this happen. Like this, no? That you see the different wavelengths, you have different paths because they have different velocities in the material. And this is an image of the dispersion of the light. But this was used in 1680s this is the first spectroscope used to know the composition of and to know what it was the elements that they make the dispersion of the light. The spectroscope was built by Kirchhoff and Bunsen, that has also a very famous in chemistry classes, Bunsen here in Brazil. And with these experiments, they saw the Fraunhofer lines. That's what happens. You see when you have an element that the light of this element pass across the prism, and you see in a screen. Then the first time that he used this as experiment, it was in 1860. These experiments, and here the spectra of different elements that you see: carbon, oxygen, iron, nitrogen. But something that is fantastic is that one of the elements that here is the periodic table of spectra that I think that Tom Field, maybe he showed it here in his presentation, because I received a gift from him with this spectra in a poster. That's a fantastic poster. And this was the fantastic experiment after the spectroscope of Kirchhoff and the Bunsen. That was the discovery of helium. Because helium, they saw the first time that they discovered the helium was when they analyzed the lights of the sun. Oh. Because in the spectra, they saw something different line. They imagined that it was sodium, but it wasn't the correct position that the spectra of sodium. Then they knew that it was a different element, and they called it helium because of the Latin word for sun, that is Helios, then the god of the sun. Then first was Pierre Janssen that made the first measurement. It was in August 1868. And then after, you have another analysis of the spectrum made by Joseph Norman, and it was in October 20. Then after this, they discovered a new element that is the helium, and received this name because of the sun. And here is what our atmosphere does here, that protects us from different kinds of the spectrum. And here you see that you are only part of visible, near infrared, near ultraviolet that cross the atmosphere, and also the wavelength, radio waves, that also cross then this is the reason that we need space telescopes to see the universe in different frequencies, that they are not the frequency that we can see from the surface of the Earth. Then it is that we need these space telescopes in the space. We have here many, we have new ones here, but here is the most famous one, that Chandra, UV, CGR, Spitzer, and here you have, we already saw the universe from the gamma's ray until the radio waves, the two parts of the spectrum that are in different positions, and they also X-rays, ultraviolet, visible, infrared, microwaves. Then you have different images here of the Milky Way in each of these frequencies, regions of the spectrum. And also I choose here some image from Chandra. You can see here in X-ray, Jupiter, Saturn in X-ray from Chandra. Then we know the universe in many different frequencies, in many different regions of the spectrum, using the space telescopes also, the help of the space telescope. And something that I think that is, I ever show this for the people here because they saw these colored images of some of these objects in space. They imagine that if you can see invisible light, you see these colors. But part of this color that we see are in the region that we can't see. Then these are false colors that we produce. Want to know if you have a big emission of these X-rays or one of the region or a small region, a region that have a small emission of these have high energies and low energies. Here, some of famous images that have in different kinds of spectrum, and then you see this, This is something fantastic, man, that but I ever ask here when they show this image to say that you have an image in different region of the spectra, and part of the region it's not visible in the visible region of the spectrum, because you have image like this, and someone can imagine that if you look, you have condition to see the visible light, you see something with these colors. That is not true. This is our position in the Milky Way. And then I show here Spectra, right? That's the infrared. And when you join the visible with infrared, you have some fantastic images that are very famous, like this one. Yes. That's a very famous one, but part of the image is in infrared. It's not invisible part of the spectrum. And here here you see the Milky Way in the different wavelengths.
That's beautiful.
Yeah. This is the universe that you see. Well, it is that I'd like to say today, and I also invite everybody to read the Skies Up magazine, the new edition. And if someone wants to send a contribution, will be very welcome for the next edition of Skies Up. Thank you very much, Scott, for the invitation.
Thank you very much, Marcelo. Thank you.
It's a big pleasure to be here. Thank you.
Oh, yeah. It's always a pleasure to have you on, too. Wonderful. Okay. When Marcelo says make a contribution, he means write an article. Because the magazine is absolutely free. And so it's free for download, and I just posted the link for it. So, but we have amazing contributors from all over the world. It is a global astronomy magazine. So thanks again, Marcelo.
My pleasure.
Okay, all right. Up next is Michael Carroll. Michael is an amazing author and one of the best space artists of all time. And I love his perspective on the cosmos. He's also extremely knowledgeable about things going on in the universe, because he has to think of ways to present accurately as much as possible what things might look like from a position that we could never go to. So that is the liberty of a space artist, but it's also the responsibility of a space artist to actually deliver the goods accurately. So I'm sure there's many people who would like to be critical of a particular view or something like that, saying, no, that's impossible, we can never see it like that, or if you did, you would never see it like that. Okay, so, but you've been doing this for quite a while, and your stuff is just pure magic. So thank you very much, Michael, for coming on to Global Star Party.
Well, thanks for having me. I am happy to be here. Can you hear me?
Yeah, we can hear you just fine.
Excellent. Let's see if you can see my screen. Where is my little keynote? Okay. I'm going to quit Keynote and start it again because that is what fixed it last time.
Yep.
Let's see here. Open research. Here we go. Okay, can you see that?
Not yet.
Okay. Aha. There.
Here we go.
How about now? Okay.
Yes.
Yes. Good, good, good. All right, let's pretend that this will work. I'm going to hit go.
Yes.
Okay.
Fine. Perfect.
Great. All right. Well, you guys, you observational astronomers out there, excuse me, you know a lot about color already, and I'm just going to go over a few things gently for those of us who are more amateur than many of you are. Of course, we've been talking about the spectrum tonight, Roy G. Biv, and all the things that light can tell us about what we're looking at. It's just fascinating to me what a spectrum can do. And what also fascinates me is the incredible organ that the eye is. The human eye is incredibly sensitive to, you know, that kind of middle part of the spectrum we talk about. But we are the exception to the rule in terms of mammals. Most of our friends in the animal world see something much more like this. The reason, of course, is that they are equipped to see better in low light levels. They need to survive at night. So what happens is a mammal that needs to see in low light levels has a lot of rods on the back of its retina. There we go. And not very many color cones. So they can't see color as well, but they can see grayscale. And this is really good for low light levels. But human eyes are built a little differently. We have a lot of color cones and they tend to block out those rods. But notice how they're centered in the middle. And there are more open rods toward the outside. This is why indirect viewing through a telescope is so good. We can see low light levels better at the edge of our vision. And let's face it, color is a wonderful thing. It adds spice to life. This is a brand new drink in New York that I just heard about, the Cruella de Vil. It looks good enough to drink.
Like
So
blood and
I know. It's a vampire drink or something.
Yes.
I don't know. But yes, we have this spectrum pouring in, some of which we can see. We can tell by light that's absorbed or emitted what the stuff is that we're looking at from a distance. And we can do that with planets as well as stars. This is Mercury. Using a stretched spectrum, we can see what the rocks are made of there, what kind of minerals are peering out of the surface. And so I want to talk a little bit about color in the solar system. This is, of course, Jupiter's pizza moon Io. Beautiful, beautiful, very volcanic, probably the most volcanic world in the solar system. It has over 600 active volcanoes as we speak. That's as many as is on the entire planet Earth, including the ocean floor. And the colors that we see are significant. The colors go from kind of tawny gray to black to orange and yellow, and even to that bright white. And these tend to line up with temperature. At 3,000 degrees Fahrenheit, 1650 centigrade, some of these vents are spewing out stuff 300 miles into the airless sky. And so you get a lot of black right at the vent. But as that cools and the sulfur mixes with silicate stuff, and the temperatures drop down to about 500 Fahrenheit, you get these oranges and yellows in the flows. And then it gets really cold, minus 200 or so Fahrenheit, and you begin to get frost from sulfur dioxide and various related things. So color does line up on Io. Here is a place called Tupan Caldera. It was named after the Brazilian thunder god. And if we place ourselves right here and look across this vast caldera, this is my version of what it would probably look like. That's Europa to the left and Ganymede to the right. But these colors are remarkable, just remarkable. There are these green sulfuric places that they call golf courses. Who could make this stuff up, you know? So it's the color is just magnificent. And if you were standing there as an astronaut, you would really see these spectra. A little bit further out, we get a lot of ice worlds. The moons are made of frozen water, and we see some patterns out there. In fact, we see a whole lot of brown. Now, Enceladus here in the foreground is the exception to the rule, but look at Europa and Pluto and Ceres, and you'll see this kind of warm coloring, which we'll see where that comes from in a minute. Here's Europa, and we have this ice crust tapping this deep saltwater ocean. We're not sure if the crust is thick or thin, like ordering pizza, you know. But one thing that is for certain is that the water makes its way up to the surface, and when it does, it explosively boils out, squirts all this water out that freezes as ice down on the surface. But then the magic happens. Europa travels through Jupiter's magnetosphere, and that radiation irradiates the stuff in the water, the impurities, and it turns it brown. So the brown stuff that we see in the outer solar system is photochemistry. Some of it is the stuff that the building blocks of life come from, very magical. So we watch for these colors, these typical brownish or rusty colors on the surfaces, and we see them all over the place. It's as if the solar system was a machine designed to create elements of life. And again, you can see it all over. From left to right, we have Iapetus and Triton, Pluto, and Pluto's moon Charon, which has probably both top and bottom big dark areas of these tholins, these hydrocarbon things. Now, you go to Enceladus at Saturn, and it's a very different case. Remember that Enceladus is responsible for the E-ring. It's squirting out all this water vapor. And what that does is it makes the surface beautifully snowy white. Enceladus is about the brightest, intrinsically brightest surface in the solar system. But it does have some color things going on. Subtle blues along these sulci, these canyons where the eruptions take place across the South Pole. The color here is slightly exaggerated, but the canyons are distinctly bluer than the ice around them. Here's a painting I did to show one of those regions erupting. These geysers look violent, and they squirt stuff 400 miles into the air, into the sky, the vacuum. But if you stood next to one and stuck your hand in it, you wouldn't feel it. The stuff is very rarefied. Remember that it's a vacuum. Out there at just above the Saturnian ring is Mimas, and from Enceladus, Mimas would be as big in the sky as a full moon is in our sky. So look how big Saturn is. Just amazing view from Enceladus. And as I said, there are places that have very blue ice, much like glacial ice, a little bit different cause, but this is a picture of the exit glacier. If we move this out to Enceladus, we'd have to get rid of that liquid water and dirt in the foreground, but we would probably see ice very similar. However, the ultraviolet light that comes down from the sun interacts with impurities in the ice, and in places where you have sodium chloride, the ice is going to turn yellow. It may be a fairly bright yellow, actually. Now we're talking about on the human scale. You probably can't see these subtleties from orbit, but if you're walking around on the surface, you're going to see that. I learned some of this when I was writing a novel about Enceladus, and Morgan Cable at JPL has done some wonderful work on the ices in the outer solar system. We also get potassium chloride, which will turn the ice purple. So imagine walking across an ice world like Enceladus and seeing purple or yellow ice. It would be just spectacular. Next out, still at Saturn, is the planet moon Titan. And it is, again, this warm color. Tholins in the atmosphere, along with the methane, cause us to see this orange, rich orange, cloudy sky. But there's something going on down below that's a little counterintuitive. Liquid methane, which rains out of the sky and turns into lakes and seas, is actually much more clear than water is. And it's going to have some impurities in it that will tint it a remarkable green in some places. So imagine seeing this green lake against this kind of orangish landscape that we saw in all the Huygens images. Yeah, just amazing. Yeah. Nature is full of surprises. The spectra can also show us changes. Watch this very carefully. The Cassini infrared imaging took these images of the changes on the surface at a site called Hote Arcus. So some researchers dismiss this as differing angles of the instrumentation, but others point to this as evidence that there's active cryovolcanism going on Titan as we speak. Of course, don't ever forget to look up at the sky. I don't have to tell you guys that. The Martian sky is beautiful. Here's an image from, I believe, Perseverance, of some ice clouds scattering spectra through them. You'll see halos and sundogs on Mars because of ice crystals in the sky. So it will be a spectacular place to sky watch when we finally get out there as scientists or tourists. We saw earlier those beautiful images, I think by was it Marcelo that took the pictures of Saturn?
It was Maxi.
Or Maxi, I'm sorry, yeah, Maxi. Yeah. And beneath the rings, you could just see the winter hemisphere was turning blue. Now, this is a natural color photo taken by Cassini of the southern or the northern hemisphere of Saturn at the time it was in winter. What happens is the clouds chill out in the wintertime and sink so that we have clear atmosphere above them tinting them more blue. So you actually get a change in the color of Saturn depending on the season. As winter comes on and things chill out, it becomes more blue above those clouds. This is a painting I did to show what those rings would look like from down within the clouds. And what about the ice giants? Talk about a weird place. We have these amazing greenish blue worlds with greenish blue skies, obviously, and the two above are of Uranus. But on Uranus, you get these things that they call tadpole storms. We see these on all the gas and ice giants, but it's a storm that develops and then drags a tail because of the prevailing winds. So below, I have put a painting I did of one of these tadpole storms, but at sunset. So imagine you get Rayleigh scattering at these places just like you do on Earth. So sunsets are going to go toward the orange, toward the red. So you'll have orange clouds against these greenish blue skies. Just amazing, magnificent things to see. So we can't go out there and see with our own eyes yet, but we can certainly enjoy this unique and dynamic and amazing planet that we are living on today, and we can enjoy the colors that we see through our telescopes. So thank you very much.
Beautiful. Now, Michael, I'm putting your stockspaceimages.com website up here. Can people buy prints of your original artwork or original artworks from you?
Yeah, absolutely. Yes to both.
Okay.
Nova Space, Nova Graphics in Tucson, Arizona sells some prints and some originals, and people can certainly talk to me through the website, and I can make available some originals or even some prints. So
Wonderful. I mean, it's just some of that stuff is just so amazing to look at, and I think that it causes the mind to kind of go on its own exploration. We see the images that we can see from observatories and amateur astronomers and the space telescopes and stuff, but to see a green lake against a yellow-orange sky in another world, that's cool stuff. So it really makes you think another way, and so I really
I'm glad.
Yeah, I'm amazed at just the kind of what's happening in my own head right now with seeing these images. So I could probably have a global star party on nothing but this. So anyhow, I really, really appreciate it, Michael. And
all right. Well, thanks for having me on.
Help us end the 126th Global Star Party. So I want to thank the audience. I want to thank all of the presenters that are on right now. A lot of them have their cameras turned off, but anyways, there's Adrian. And anyhow, we will be back next week, next Tuesday, for the 127th Global Star Party. So watch for the announcements on social media. And until then, keep doing as my friend Jack Horkheimer always used to say, and that is to keep looking up. I do have a little featurette from NASA about the sun and the light emitting from the sun, and so I thought that would be a good way to end this. But again, thanks for watching from all over the world, and we'll be back next week.
The sun is a star. It's a star that we often describe as average, run-of-the-mill, just ordinary. Yet this ordinary star is responsible for helping to sustain all life on Earth. No other star that we know of has that level of responsibility, and that's pretty extraordinary, if you ask me. The Sun is a living, breathing star. It is active, dynamic, and ever-changing, just like us. Its influence can be felt in every aspect of society, from agriculture and economics to arts and culture, as well as the physical, mental, and emotional health of human beings. The Sun touches everything. And to highlight the importance of our extraordinarily ordinary star, NASA is hosting the Heliophysics Big Year. Beginning with the annular solar eclipse in October of 2023, continuing with a total solar eclipse in April of 2024, and ending with Parker Solar Probe's closest approach to the Sun in December of 2024. The Heliophysics Big Year is a global celebration of solar science and the Sun's influence on everything. Over the course of the year, we are challenging everyone, including the public, the science community, and you, to participate in as many Sun-related activities as possible. Heliophysics is the study of the Sun and its influence on, well, everything. NASA has a fleet of strategically placed spacecraft that work alongside other missions from NASA and space agencies around the globe to monitor the Sun 24/7. Together, we are working to increase our understanding of solar phenomena such as solar flares, the solar wind, and space weather. We have missions studying everything from Earth's uppermost atmosphere, where the International Space Station lives, to our 45-year-old Voyager mission that is investigating the outer boundaries of our solar system. We've even had one mission that has actually entered the Sun's atmosphere. Parker Solar Probe touched the Sun. Studying these complex systems helps us better understand our universe, including our solar system, distant stars, exoplanets, and our search for life on other planets. Understanding the Sun's activity is critical to all of NASA's endeavors, especially our human exploration efforts. It underpins our Artemis missions, enables us to protect technology on Earth and in space, helps safeguard our astronauts, and allows us to voyage to Mars and beyond. The Heliophysics Big Year is a unifying effort designed to encourage exploration, creativity, and wonder. We invite you to engage in the world around you with intention and curiosity. We invite you to experience the annular and total solar eclipses with us. We invite you to do science and to experience our Sun in different ways. Throughout the year, there will be opportunities for communities across the globe to participate in Sun-related activities such as experiencing solar eclipses and auroras, joining citizen science projects such as HARP and Spritacular, creating Sun-inspired art, music, fashion, and food, and a host of other fun heliophysics activities. So please join us for the Heliophysics Big Year and help us celebrate our extraordinarily ordinary star.